Welcome to the Deep Dive. Today, we're taking you, our listener, on a journey, a deep dive into inertial frames. And as a philosopher, you might be thinking, inertial frames? That's physics, isn't it? Yeah, you're right, but stick with us. This seemingly simple physics concept is going to open up some pretty profound philosophical questions that we're going to explore today.
You see, inertial frames are more than just equations and calculations. They touch upon these fundamental questions about motion. Like, what even is motion? How do we measure it? Is there even something like absolute motion, or is it all relative? And these are questions philosophers have been grappling with for centuries.
So much depth to unpack. But before we get ahead of ourselves, let's start with the basics. Can you remind us what an inertial frame actually is?
Absolutely. An inertial frame, at its simplest, is a reference frame where if an object is at rest, it'll stay at rest, and if it's moving, it will keep moving in a straight line at a constant speed unless some force acts on it. Like, picture a spaceship just coasting through space with its engines off. That's a classic example of an inertial frame.
Right, so it's like a setting where everything behaves how we intuitively expect. No sudden accelerations or changes in direction unless there's a force behind it.
Precisely. And here's the thing, this seemingly simple idea has a long and complex history, and that's where the philosophical implications really start to emerge.
Well, let's rewind the clock then. Where does this story begin?
Let's go back to the 16th century, to the time of Copernicus. Now, his heliocentric model, putting the sun at the center of the solar system, wasn't just a big deal for astronomy, it was a philosophical earthquake. It shook how we saw our place in the universe.
I can see that. It challenged this idea that the Earth was this privileged reference frame, the one and only correct place to view everything else from.
Exactly. And this shift opened up so many questions. If Earth isn't the center, then what reference frame should we use? Is there even a correct frame of reference, or is it all just a matter of perspective?
Now we're getting to the heart of it. This reminds me of Leibniz's idea about the equipollence of hypotheses. He argued that, in theory, anybody could be considered at rest, and the laws of physics should look the same from any of those viewpoints.
That's a really important point. Leibniz was basically saying motion is relative. There's no absolute standard of rest that everything else is measured against. It was a radical idea, especially compared to that mechanical philosophy that was popular back then, which depended on the idea of a privileged state of motion.
So we have this philosophical battleground set up. Then comes Newton, trying to make sense of it all, right?
Exactly. Newton wrestled with these very questions, and his work is the basis for how we understand motion and inertial frames today. He introduced the concept of absolute space, this invisible framework that true motion is measured against. You can think of it like a cosmic grid that everything moves against.
But didn't Newton also recognize the relativity of motion? We have the principle of Galilean relativity, which says that the laws of mechanics are the same in all inertial frames.
That's the fascinating tension at the core of Newton's work. He understood that inside a specific inertial frame, you can't tell if you're moving or not just by doing mechanical experiments. Galileo's famous ship experiment shows this perfectly. Imagine you're below deck on a ship moving at a constant speed. You drop a ball, it falls straight down, just like it would if the ship were at rest. No experiment you can do inside that closed system will tell you if you're moving or not.
So there's this equivalence of inertial frames. But then why did Newton hold on to this idea of absolute space?
It's a question that has puzzled scholars for a long time. It's a complex issue. Part of it might have been that he needed a conceptual anchor. For Newton, forces needed something absolute to act against. Like when you push a shopping cart, you need the solid ground to push against. Absolute space, for Newton, provided that solid ground for forces to act on.
So he saw that motion within a specific frame is relative, but he needed absolute space to ground the whole system. But if he understood relativity so well, why not just go ahead and define inertial frames?
It would take a while to get there. Even though Newton did the groundwork, the formal idea of an inertial frame, as we know it today, didn't really come about until the 19th century. It took the work of later physicists and mathematicians to refine and really solidify this concept.
So who were these pioneers of inertial frames? Tell me more about them.
Thinkers like Newman, Lange, and James Thomson, they all grappled with defining these inertial systems. Newman, he used the concept of multiple free particles, particles that aren't affected by any forces, to define a timescale. Imagine two of these particles. Equal intervals of time are when they travel distances that are proportional to each other. Then, Lange, building on Newman's work, used that to define inertial systems themselves. He said you need at least three free particles moving in straight lines to define such a system, and any other free particle would also move in a straight line in that system.
It's amazing how they use these abstract thought experiments to come up with a definition. But wasn't there a different approach, too?
Yeah, there was. James Thomson, he offered a more practical approach, focused on observable forces and the center of mass of a system. He was interested in defining inertial frames not just for these ideal free particles, but for real systems with interacting bodies, like the ones we actually see in the world.
So by the end of the 19th century, the concept of an inertial frame was becoming more solid. But this is just the beginning of the story, right? What happens next in this philosophical journey?
Well, just as physicists were getting comfortable with inertial frames, a whole new set of challenges popped up. Challenges that would once again shake the foundations of physics and lead to a whole new way of understanding space, time, and motion.
Welcome back to our deep dive on inertial frames. When we left off, physics was about to get a major shakeup. Time to bring in the big guy, Albert Einstein, and his revolutionary theories of relativity.
Yeah, you're right. We can't talk inertial frames without diving into Einstein. But before we get to the complexities of relativity, let's picture how physicists were thinking about these frames in the early 20th century. Imagine this four-dimensional space-time. It's like a map, but each point on it shows not just a place in space, but a moment in time, too.
Okay, I'm trying to wrap my head around that. So it's like a 3D map, but with time added in as the fourth dimension.
Exactly. Now, in this four-dimensional picture, inertial frames are represented by these families of parallel lines. Each line shows the path of a free particle moving at a constant speed.
So a whole bunch of parallel lines, like a whole family of them, represents a single inertial frame, showing all the possible paths a particle could take when no force is acting on it.
Exactly. But here's where it gets interesting. In Newtonian physics, there was this idea of absolute time. Imagine slicing up this four-dimensional space-time into a bunch of 3D slices. Each slice shows all of space at a single moment in time. These slices were thought of as hypersurfaces of absolute simultaneity.
So you're saying that in Newtonian physics, everyone, no matter where they are or how fast they're moving, would agree on what events are happening at the same time. Like everyone's clocks are synced up in this Newtonian universe.
That was the idea, and this assumption had some big implications. It meant lengths and durations, how long something is, and how much time passes were considered absolute, the same for everyone, no matter their reference frame.
Yeah, that makes sense from our everyday experience. But I know this neat picture starts to fall apart when we add a new element, electromagnetism.
You got it. By the late 19th century, physicists had this great theory of electromagnetism, Maxwell's equations. And these equations seem to suggest a preferred reference frame, the rest frame of the ether. The ether was thought to be this medium that light waves traveled through.
Ah, the ether, the mysterious stuff that supposedly filled all of space. Seemed logical at the time. After all, if light is a wave, it needs something to wave in, right?
That was the thinking. But every attempt to actually detect this ether, to measure our motion relative to it, failed. And that created this huge conflict between electromagnetism and the principle of Galilean relativity. If the speed of light is constant relative to this ether, shouldn't we be able to detect our motion through it?
Sounds like physics had a big problem on its hands. How did they solve it? Enter Einstein, right?
Right. In 1905, Albert Einstein completely changed our understanding of space, time, and inertial frames with his theory of special relativity. His solution was brilliant and radical. He said the speed of light is invariant. That means the speed of light is the same for all observers, no matter how they're moving relative to each other.
Whoa, that's mind-blowing. So if I'm standing still and measure the speed of light, and you're flying past me in a spaceship at half the speed of light and measure the speed of light, we get the same result. How does that even work?
It's pretty wild, but that's the core of Einstein's insight. He realized that for the speed of light to be constant, something else had to change. And that something was our idea of absolute simultaneity.
So the idea of universal now, where everyone agrees on what events are happening at the same time, that's gone.
Exactly. Einstein showed that events that are simultaneous for one observer might not be simultaneous for another observer who's moving relative to them. Simultaneity becomes relative. It depends on the observer's frame of reference.
This is incredible. But if there's no absolute simultaneity, what does that mean for how we understand space and time?
It has some really big consequences. It means length and time aren't absolute quantities anymore. They're relative to the observer's reference frame. What looks like a certain length or duration to one person might look different to someone else who's moving at a different speed.
So our measurements of space and time are all tangled up with our motion. It's not just where you are, but also how fast you're moving that matters when you describe events.
So how did this change the idea of inertial frames? Einstein redefined inertial frames with special relativity. They weren't about force and acceleration anymore. Now they're defined by the constancy of the speed of light. An inertial frame is any frame where light travels at the same speed in every direction.
So Newton's inertial frames were about objects moving uniformly. Einstein's are all about the speed of light staying constant. But are inertial frames still important with this new definition?
Absolutely. In fact, they're key to understanding how different inertial frames relate to each other. These relationships are called Lorentz transformations, and they show us the interplay between space and time in special relativity. They tell us how lengths contract and time dilates as things move closer and closer to the speed of light.
It's amazing how Einstein's work completely changed our view of reality. We've gone from absolute space and time to this world where simultaneity, length, and time are all relative. But didn't he go even further? What about general relativity?
You're right. Special relativity was just the start. Einstein wasn't satisfied with a theory that only worked for inertial frames. He wanted one that could handle all frames of reference, even accelerating and rotating ones. He wanted a theory that could explain gravity not as a force, but as a curvature of space-time itself.
So that's where general relativity comes in. But if general relativity is about all frames of reference, do inertial frames even matter anymore?
That's a great question. The role of inertial frames in general relativity is subtle, but they're still important. To understand this, we need to talk about a key principle in general relativity, general covariance.
General covariance. Sounds intimidating. Can you break that down for me?
It's a powerful idea, really. General covariance says the laws of physics should be the same in all frames of reference, no matter how they're moving. The laws of physics shouldn't depend on how you choose to describe them, your choice of coordinates.
So it's like saying the laws of physics are coordinate independent. They describe some objective reality that's out there, no matter how we choose to observe it.
You got it. This principle of general covariance led Einstein to develop general relativity, where gravity isn't a force, but the curvature of spacetime itself. Massive objects warp the fabric of spacetime, and this warping affects how objects move, which is what we experience as gravity.
Okay, so where do inertial frames fit into this picture of curved space-time? Are they still useful?
That's where things get really interesting. In general relativity, inertial frames become these local approximations of a much more complex reality.
Local approximations, what does that mean?
Imagine you're standing on a really big curved surface, like the Earth. If you zoom in close enough, the surface seems flat, right? You can use a flat map to get around a small area pretty well, even though the whole surface is curved. It's similar in general relativity. We can often define these local inertial frames that work well for describing how things move in a small region of spacetime.
So even though space-time is curved overall, if you look at a small enough piece of it, we can still use the tools of special relativity, which are based on inertial frames, to describe what's going on.
Exactly. These local inertial frames are really important tools. They let us make predictions, analyze what we observe, and understand physical stuff, even within general relativity. They're this powerful bridge between the flat spacetime of special relativity and the curved spacetime of general relativity.
This is amazing. So inertial frames have gone through quite a journey, from these absolute frameworks in Newton's physics to relative ones in special relativity, and now to these local approximations in general relativity.
Yeah.
This has been such a fascinating look at how this concept has evolved. Is there more to the story?
There's always more to explore. We've covered a lot, but the philosophical implications of inertial frames are huge. Come back for the final part of our deep dive where we'll tackle some big questions. What does all this mean for how we understand objectivity? If our descriptions of the universe depend on our frame of reference, is there even a true reality out there?
Welcome back to the deep dive. We've been on quite a journey, haven't we? Tracing the evolution of these inertial frames from Copernicus to Newton, and then all the way to Einstein and his mind-bending theories of relativity.
It has been a fascinating exploration. We've seen how these seemingly straightforward frameworks for describing motion have really led us to question some of our most basic assumptions about space, time, and even the nature of reality itself.
Absolutely. But after all of this, I still have some of these philosophical questions lingering in my mind. Like, if general relativity tells us that space-time is curved, does that mean inertial frames are kind of like illusions? Do they actually exist, or are they just these convenient fictions that we use to try to make sense of a more complex reality?
That's a really deep question. It gets to the heart of the relationship between the theoretical models that we create and the physical world that's actually out there. Inertial frames, even within general relativity, they're still super useful tools. They let us make predictions, analyze observations, and understand physical phenomena in a consistent way.
So it's like we're using these flat, idealized frames to try to map this curved, non-uniform reality. But if those frames are just approximations, does that mean our understanding of physics is somehow flawed or incomplete?
Not really. Think about it this way. All scientific models are, to some extent, approximations. They capture certain aspects of reality, but they kind of have to ignore others. The key is to understand the limitations of the models that we're using and to use them appropriately. In the case of inertial frames, they're remarkably effective for describing a lot of phenomena, especially in those regions of space-time where the curvature isn't that strong.
This reminds me of something we talked about earlier. Newton, even though he introduced the idea of absolute space, he also recognized that in practice, we can only work with these approximate inertial frames.
That's a great point. Newton was very pragmatic. He understood that there's this interplay between these theoretical ideals and the practical limitations that we face. He was able to develop this incredibly powerful and predictive theory of gravity without having to pinpoint some truly inertial frame. In a similar way, physicists today continue to use inertial frames as these essential tools for understanding the universe, even though we know they have limitations within the broader framework of general relativity.
So it seems like inertial frames kind of occupy this interesting middle ground. They're real in the sense that they are effective tools for describing physical phenomena, but they're not real in the sense that they're not these fundamental building blocks of reality in the same way that, say, energy or momentum might be.
Yeah, that's a good way to put it. It's kind of like the relationship between a map and the territory that it represents. The map is a useful tool for navigating the territory, but it's not the territory itself. In the same way, inertial frames are useful tools for navigating the universe, but they're not the universe itself.
That brings up this really fascinating question about objectivity. If our descriptions of the universe depend on our choice of reference frame, does that mean there's no such thing as an objective view of the universe? Is it all just relative?
That's a question that has kept philosophers busy for centuries, and it gets even more interesting in the context of modern physics. General relativity, with its focus on general covariance, suggests that there is an objective reality out there, but our descriptions of that reality will always be influenced by our own perspective.
It's like that classic story of the blind man and the elephant. Each man touches a different part of the elephant and comes away with a completely different description. But the elephant itself is still real, even though each individual perspective is limited.
That's a great analogy. It really highlights how important it is to recognize that there are multiple perspectives. We need to understand that our own individual viewpoints, the frames of reference that we choose, can only offer us a partial glimpse of the whole picture.
So what does this all mean for us as observers who are trying to make sense of the universe? Does the relativity of inertial frames kind of undermine our search for objective truth?
I think it emphasizes how important humility and open-mindedness are in our quest for knowledge. We need to be aware of the limitations of our own perspectives and how the models and frameworks that we use shape our understanding. But at the same time, it's also a reminder of how amazing human ingenuity is. We've developed these incredibly sophisticated tools for exploring the universe. And even though our descriptions might be relative, they've allowed us to discover these deep and profound truths about the nature of reality.
It's a humbling thought. Even some of our most basic concepts, like these inertial frames, are ultimately just tools. They're not the final answer, but they help us to grasp at the edges of reality, to kind of get a glimpse of its hidden depths.
Exactly. And the exploration doesn't stop here.
Yeah.
The philosophical questions that these inertial frames raise, people are still debating and exploring them. They push us to confront the biggest mysteries about space, time, and our place in the universe.
Well said. Listeners, we hope this deep dive into inertial frames has left you with a sense of wonder and a desire to keep exploring. Remember, the universe is this vast and mysterious place. Keep questioning, keep exploring, and keep diving deep.